Hey, I'm making this video to talk about what you missed, if you missed the sulfur lab, the allotropic forms of sulfur lab, or if you just want a little bit of a review with what we saw in the lab and what that means as far as properties and how what is happening at the molecular level can result in those properties. So just a reminder that an allotrope or allotropes are different forms of the same elements. Oh, this thing did that again. I wish I could figure out why it keeps making those lines. And I'm writing kind of in a sulfur colored ink, just for fun. So in the very first part of the lab, we took some powdered sulfur, and this is orthorhombic sulfur powder. So I want to remind you that a sulfur molecule has 8 sulfurs, and those 8 sulfurs are arranged in a ring. I hope I have 8 there in a ring like that, and if you were to put it on its side, it kind of looks like a crown. 1, 2, 3, 4, 5, 6, 7, 8. I don't even know if I have 8 there, but it would kind of look like that. But they're 8 ringed structures. So to represent this ringed structure of a sulfur molecule, I'm just going to use a circle. So orthorhombic sulfur, the crystals are very short and blocky. So just kind of showing you that we have very short crystals. And the atoms, the molecules, will be arranged in an orderly way that is also very short and blocky. And that's why the structure of the crystals, if we could see the crystals, would also be seen on a macro scale. If we could see the crystals, we would see these short blocky crystals. So that is orthorhombic sulfur. And we gently heat the sulfur to form the liquid allotrope of sulfur called lambda sulfur. And you can see it melting there, gently melting at gentle heat. And we get this structure here, and this is the lambda structure. And now those rings are still pretty close together, not in an ordered fashion, and they can move past each other and slide past each other and roll around. So I made this one a little bit littler because I want you to imagine it kind of further in the distance, so adding some 3-dimensionality to it. Okay, so we still have our ringed structures, and they're just rolling around. I have my special glove, so my tablet doesn't make the lines that it's making anyway, so it's not helping too much. So the molecules are still in a ring structure, and they just kind of slide past each other. They can move freely in this liquid, and it's a nice and runny and smooth. It's kind of like marbles, can very easily slide past one another. And then as we poured this lambda, this runny honey-colored lambda sulfur into filter paper, and as it started to cool, we started getting monoclinic crystals. And you can see the very long needle-like crystals here. So what's happening now is the sulfur molecules are aligning themselves in an ordered structure, but it's not a short and blocky structure anymore. They are going to be in long rows. They're rigid, they're stuck in place, they're still rings, and maybe eventually we kind of come to a point. Okay, so this is monoclinic allotrope of sulfur. All right, and here are some beautiful needle-like crystals in which those molecules are arranged in rows. long skinny rows, like my fingers, which are kind of short and pudgy actually. All right, the next thing that we did is we heated some of the orthorhombic sulfur intensely. Now what this does is it causes the sulfur ring, so this is lots of heat. The triangle in chemistry class means lots of heat being applied. It's the Greek delta symbol, I think. So it takes these ring structures and breaks them into chains. I'm trying to get it into the camera so you can see. It just breaks them into chains, okay? Breaks them. So now, instead of a ring structure, we have sticks. So they're chains. So as in here, the liquid is made of sticks because all of those rings have broken. Maybe there's a ring here and there, but the liquids broke, these rings broke into sticks, and those sticks are constantly like hitting up against each other, and it makes this liquid very, very thick. It's not like the thin runny stuff where those marble-like things could just roll past each other. Now we've got sticks, and they hang up on each other, and that's why this liquid is so thick. Also, the light is hitting it differently, so the light is hitting this different structure in a different way, so that light is reflecting the dark color. So just changing the arrangement and the shape of the molecules results in, number one, that liquid being very, very thick, this mu sulfur, which is this allotropic form of sulfur, but also the rings they're also a different color. So up here we have some vapor, sulfur vapor. The atoms are really far apart and they can move. Okay, and then we quickly cooled this. Actually, you can see that this one ignited here. There's some flames. We quickly cooled it into amorphous sulfur. And what happened is these sticks were frozen in place. So with amorphous sulfur, these sticks are frozen into place. Amorphous sulfur. There may be an occasional ring here and there. Now slowly over time, both monoclinic sulfur and amorphous sulfur, if this is the monoclinic and amorphous, will slowly turn back to orthorhombic. So here's that amorphous sulfur again. If we could have the atomic arrangement here, we would have sulfur chains, no orderly arrangement, solid, which makes it amorphous. And here's our monoclinic. Another really neat picture of that amorphous sulfur. And over time, you can notice that these are both starting to get dusty looking because they are very slowly over time turning back into that orthorhombic variety, which is a more stable form of the sulfur allotrope. So a summary, orthorhombic sulfur is a pale yellow powder. That's what we saw. It would be blocky, chunky crystals if we could see the crystals. The lambda sulfur was the runny orange yellow liquid. It consisted of rings that could move freely and slide easily past each other. This consisted of rings that were arranged in a blocky way. The monoclinic were rings that were arranged in long, skinny crystals. That the molecules arranged themselves like that. Mu sulfur, the rings had changed into chains, and these can move past each other and click into each other, and that's why this is very thick. And then the amorphous sulfur is these chains just kind of frozen into place. And then the sulfur vapor mist would be sulfur molecules that were really far apart from each other and able to move freely. So these 1, 2, 3, 4, 5, 6 allotropes of sulfur. There were no chemical changes that took place in this lab. The only time a chemical change could have possibly occurred is in this situation right here where this ignited and the sulfur started to burn. That's not a desirable part of this lab. Wasn't supposed to happen. Sometimes it does, but these are all physical changes that involve melting, vaporization, and recrystallization as these energy transfers take place when we add the energy, and then the energy leaves the system as a system is cooling down. So that summarizes my there, you can see my face bigger. That summarizes my allotropic forms of sulfur lab, talking about the properties of the sulfur, why the structure at the molecular level is contributing to those properties. Thanks for watching.